And now it gives me great pleasure to introduce to you Chris Barrett from the Los Alamos National Laboratories. He is the founder and present group leader of the Basic and Applied Simulation Science Group of the Computing and Computational Sciences Division at Los Alamos. And he's one of the world's leading experts in the simulation of complex systems and is now involved in the simulation of very large-scale complex systems like transportation systems, healthcare, or I should say public health, energy systems, and communications. So let's welcome Chris Barrett. Thank you.
I think I have a mic. Am I mic'd? I think I'm mic'd. Okay. So thank you very much to the organizers for inviting me to come. I'm honored, although it's hard to follow Lord May. It's not too, that wasn't very nice. I was going to take this off. I decided to leave it on because I think the last talk was a perfect setup for a lot of things. I feel like I have to defend myself practically, but it's absolutely right. It is possible to do nothing with computer simulations and claim it to be a lot more, I suppose. On the other hand, one of the things that I'm going to talk about in this talk is whether or not simulations are optional. I'm going to talk about them as a species of computation. And I'm going to talk about them in a sense where what I mean by simulation, I need to make that a little bit clear here at the beginning, because there are times when it's used almost synonymously with the concept of model. But a modeling relationship is just a representational relationship, and it really hasn't anything to do at all with computers. And they certainly aren't necessarily simulations in the sense I'm talking about. So I'm talking about this interaction-based computing. I'm talking about the explicit calculation of interactions among individual elements. So I just want to be clear about that. It's a theme. I'm not talking about, for example, writing a model down in the form of, say, an epidemiological model if it were written in the form of systems of partial differential equations. Sometimes, as we all know, it's very tricky to get them to be calculated, and that's very nice, but it's a model, and it is not a simulation necessarily by these kinds of use of the term. So, you can't hear me? I'm sorry. I'll get the microphone closer to my head. Is that better? Good, okay. I'll talk like this. Okay, so some of the things that come up, you hear about things called agents. When you talk to software people, a lot of times an agent is really a direct step to object-oriented software, and just to be maybe a little bit overly pedantic here, object-oriented software, you have encapsulated objects where you have procedures and data local to the object. It's a wonderful software paradigm, and it does, in fact, if you want to, apply to the effective commingling of the concept of a software object and an agent, because you can make an agent a software object. But on the other hand, it has nothing whatsoever to do with agents, and they get pretty heavy, and you can't calculate really, really lots of those. And so the simulations I'm talking about doing have millions and billions and even trillions of interacting agents, and although we use object-oriented software, we don't use it for that. So I don't want you to be confused. I'm not just simply talking about object agents. I'm not talking about bots necessarily. I'm talking about a very abstracted concept of agency where you have locality and you have the capability to interact with other agents. And there's a lot of ways, some of them very abstract, to achieve that. And that's the point, is that what you want to do is you want to create these interaction environments, and you want to compose big systems out of them, and you don't want to do it in a way that is, as we heard about, vacuous or empty-headed. You want to do it in situations where you need to. and where you learn something from doing it, and where it, and moreover, we want to understand, as you see in the last bullet, because I'm not really going to go on too much more with this incredibly boring slide, we really do have to understand what we're doing when we calculate large systems of interactions. That is a topic. It is a mathematical topic. And what we're trying to cast here, and what I'll show you at the end, is the fact that this topic can be cast and studied on its own basis, and it turns out to be actually very beautiful if those kinds of things matter to you. But it also is, and perhaps more importantly from the purposes of keeping yourself, funded and things, useful. So I'm going to start actually by a little bit more of this, and then I'm going to show you lots of reasons that we use these things, and we'll talk about it in very practical terms, and at the very end, I'll slime over into the outside hull of what the theoretical structure of these things looks like, and I'll tell you how we use that for things like specification and design of these big simulations, so that you understand what they are, so that we understand what they are. Okay, so that the basic idea is that you need some entities, and they're going to be interactors, but you have entities and they're characterized by state. They interact with other ones, which causes their state to change. There's compositions of those interactions, or rules of composition, or laws of composition, depending on what you mean by interaction and what you mean by entity, but there's compositions of these interactions, and these result in system realizations. And this is nothing really new. In fact, if you take an n-body dynamics sort of a code and you put it in this framework, the entities are particles and interactions are collisions, and you have exchange of momentum, and you have conservation of momentum, and you have system realizations that are n-body dynamics. And it's pretty well known what's good and what's hard about these kinds of things. In this case, a lot of times it's an optional way to approach the calculation, sometimes it's not. But with the same underlying sort of architecture, or whatever you want to call this, framework, you can have players that possess information, they have actions and strategies. The result of their interactions, which result in payoffs, that you use some sort of equilibrium criterion if you're doing game theory, and you wind up with game realizations, and so game outcomes and realizations. And so what you have here is you have the same sort of underlying structure, and I would really rather not have the physics of games or the games of physics. What I would really rather have is an underlying theory that I can do interaction-based systems with, whether they're games or particle codes. But moreover, most of the systems we calculate most computer systems that we calculate these very large socio-technical systems or biosystems on are massively parallel machines. And they themselves are, in this sense, simulating a computer or a computational entity. And the entities are compute nodes, the states are memory values, message passing is a form of interaction, we have these things. And the point is this, is what we're really about is we take one interaction-based systems, which we approach by specifying it in a way that I'll describe as we go on, and we map it onto this one. And what we want to know is, can this device capture the dynamics of the first one? And that's the basic framework, and I'm going to ignore this one. So I'm going to give you now some examples, and then we'll get back to what the theoretical program looks like that helps illuminate why it is that you would do this, should do this, might do this, and just give you an example of some of the things we do. So, the thing I'm going to talk to you about is interactions among operating civil infrastructures. The scale that these happen on is on the scale of entire urban regions. So, like metropolitan London, the Los Angeles Basin, metropolitan Chicago, the Washington to New York corridor on the east coast of the United States. There are millions, tens of millions of people in there. We simulate, in certain areas of this simulation, we simulate every single individual. And we update them once a second. And it depends on what you're doing by what you mean by update. But by and large, what we do is for reasons that are motive-driven, activity-based, we change their positions and the characteristics of the activity they're engaged in. We don't do things like simulate their legs or something. I mean, there are things we don't do. But we motivate where they are and what they're doing once a second. In certain places. In other places, it's a bit more aggregated. So it's a big multi-scale thing. The time scales that this operates on is on the order of decades to tenths of seconds. The spatial scales are obviously large and various. And it is not one big monolithic thing. These are all simulations that are created to interact. And so the question is, and the primary user of this information right now is for good or ill. These are Homeland Security related issues. Is the cascade of effects, not just catastrophic effects, but the cascade of effects that propagate among these sectors and within these sectors for a lot of different reasons. It doesn't have to be, an attack. It can simply be a policy that is put in place to stop them. You want to know, will they stop harm from propagating in these systems? Will those policies work? So that's the basic system. To be really redundant, we have telecommunications sector, which includes wireline and wireless, including next generation style wireless, like ad hoc networks and so on, in a lot of detail. Public health sector is purely associated at the moment with the representation and the representation of the interventions in epidemiological phenomena. The transportation sector is a full-blown intermodal end-to-end transportation simulation. The only financial sector thing that we have associated with it happens to be a large commodity market representation for the energy sector, and I'll get to that in a minute, but it's multiple markets. Bilateral markets, forward markets, spot markets, in interaction and with traders, and it's taken down to the individual address level. So the energy sector is all the generators down to 69 kV. In the United States, that is down to substations, and then we model the distribution down to addresses using other methods that are less highly resolved. Now, just to give you an idea, I'm not going to keep showing you pictures like this. I hope this is the last one like this I show you. And I talked about an agent. So a person has certain properties and certain constraining relationships with other persons, and certain things they have to do, and certain ways they can go among the places that they have to be to do those things, and then they have to see if the system will service their ability to do the things they need to do. So it turns out that when you turn on the activity-based simulation system, it sort of turns the pulse on in the infrastructure. If what your question is how is the infrastructure working, the real question is it servicing activities, or are activities being stopped by interruptions in service provided by the infrastructure? So the infrastructure really provides resources in organized ways, and interruptions in the infrastructure eliminate those resources, and therefore activities are interrupted. So you monitor activities to measure the function of the infrastructure. You don't monitor, you can monitor the infrastructure, but it doesn't really tell you very much. So a person, an individual, a me, has many different faces. And among those faces, many different features and characteristics that are detailed facts associated with them. So, speaking phenomenologically, you have certain functions and you have certain facticities, and you are a trajectory over these modules. A single agent, can interact with others in determining the constraints on their access to a vehicle or where they happen to live. And other constraints apply to how they plan their days, like how the roads are configured. And then when they wind up in traffic on tenths of seconds, it affects how they actually realize those things. So these are big feedback structures where we get representations of you based on fractional information from lots of little pieces. The simulations pull all these things together where you really haven't ever collected this data in detail, and creates large populations of millions and millions of little individuals that know how to interact with one another at these various levels and adapt themselves to be able to put this heartbeat, as I told you, into the infrastructure. And at that point, we can figure out if you're using energy at the places that you need to be because you got there. what the loads you're causing on the telecommunication system are, if you're sick, where it is, who it is you're sneezing on, and so on. So, so transportation is actually a little more central than the other ones. But so to go on, this is a coordinate system for Portland, Oregon. It looks like a map of Portland, Oregon, but actually, well, it is a map of Portland, Oregon, but it all comes down to activity locations and movement between activity locations, and so that's actually the coordinate system for Portland, Oregon. This map, when it's fully elaborated for the most intensive use of the relationships among pieces, is a map that we have to do things like define paths through and stuff like that. That map has 4 million edges in it in Portland, Oregon. So if you think about it from the point of view, if you're computer science oriented, you think about it in terms of pathfinding algorithms and so on. You have to do some really fancy stuff to figure out how to deal with stuff like this. You don't just throw computers at that because it won't matter. It's too hard. The coordinates in that coordinate system are activity locations, and this is gives you an idea of what we have. We have all of the built infrastructure down to every single address, and we know what the activity types performed in those addresses are, and sometimes they change by time of day if it's a big multi-use facility. So you have a place where people work and live and have shops and stuff. It'll change by time of day. So this information, as I keep saying, comes from a variety of different sources. Nobody ever collects any of this in a way that was intended to be integrated, and the simulation is what's going to pull all this stuff together, and I'll show you. But anyway, that's what we mean by, in this particular case, when you start to really think about what you're going to do in a simulation, and you're going to have an interaction-based whatever the heck, you really are talking about going in and doing some really hard sort of blue-collar work to get down to the level that you need to be before you can start. Now, in those places, we have to initialize, if you will, the agents or the interactors, the objects that are going to be interacted. So there's lots of different kinds of interactors, but we'll talk about the population. To start, you have to initialize the basic structure of what you're going to call an individual. So for purposes of this particular kind of interaction, what we need is a localized demographic vector, is what it amounts to, associated with an activity list that is associated with a location list. So that's what we're going to construct. So we go to things like census information, marketing surveys, other kinds of things, and we'll talk about it in terms of the census. It's kind of like this. It means other information, but you have a matrix, and it has marginals, and the n-way tables are suppressed for privacy. So what we do is we rake those tables, and we refill the n-way. We rake the marginals, and we refill the n-way tables with populations that have the same demographic structure. So if you sampled them, you get the same census. And we do that. We make thousands of them because it's non-unique. And so up to the measure that we have, up to the accuracy of the census and the marketing surveys and so on, what we have is a population that up to what we can measure, it's isomorphic. It is not exactly right, but it's incredibly detailed. So some of those populations, when we start to go ahead, if you try to actually realize them in the simulation, they won't work because they match the data, but they don't really represent what the actual population is, and so as we go forward, they don't work. And so you use feedback mechanisms to modify them and prune them and throw the ones away that don't work and correct them. You wind up with a very highly refined population that doesn't only match now the data that you do have, it does match that, but in addition to that, it also satisfies all the constraints associated with this really complicated stuff that never anybody thought had anything to do with this, the census, for example. In the end, you wind up with household structures, for example, lots of different kinds of structures, but here's a household structure of some guy and his family, and they have relationships. And this guy has a Ferrari, so he makes $37,000 a year, so he is like a drug dealer. But, or maybe that's a contouch, I don't know what that is. So he's a, but in any case, these people they have 68, the basic place we start, there are 68 demographic variables, and these are, some of them. And then they have relationships with other individuals that would characterize how the census says this stuff. So we generate them as individuals, and then we start to hook them together. And the reason that they'll start to constrain things is like if little Johnny here needs to go to school, somebody's got to take him, and it will affect their activity structure. And so it'll affect the way they start to utilize the infrastructure. But at this point, all we know is that somebody's got to take the metro, somebody's going to drive the car, and Johnny's got to get to school. We don't know that yet, but we can set up the constraints over the relationship among these people. In other words, the first order, rather static interaction structure starts to form when we make these kinds of units. There are work units, carpool units, household units, family and non-family units. There are 36 different kinds of fundamental elements that structure these individuals. And then you go in and you find the appropriate place for these structured families in the land use information you have by block group by block group, address by address. You put in the right kind of organization, human organizations into those places, and now they're constrained inside the coordinate system. The coordinate system has now been loaded with things that have motive. We haven't given them any way to actualize their motive, but they're stuck in these places and they're distributed in that coordinate system. So now if this guy wants to go to work, he's going to have to interact with this system in ways that are specified, but there are millions of these guys, and so it gets to be a really complicated question. And the idea is, can you aggregate it? Can you just write it down in a systematic, more aggregated form and solve it in a useful way, or do you have to do this? And it's a long story, but for certain questions, you do have to do this. Okay, so what you wind up with in the end is, this is just a picture of what the initial conditions are of these interactor guys. The colors represent the kinds of household structures or non-household structures there are. These are not at work. This is initial, so you have to have something to call initial, so we put them all at home. The height is how many there are. So the next thing you have to do is every one of those guys has an activity list. So they all have date timers, and so somebody's going to go home and doctor and work and lunch. And these patterns come from travel surveys and, again, other kinds of information from facilities that keep track of who's going there. Like I won't go into the details of that, but there's a lot of information about what people do in the day. Micro-marketing companies can pull this sort of stuff out. We pull it out. There's a lot of ways to do it. Anyway, we make everybody a date timer. Then we route them through the constraints of the transport system, which has walking and bicycles and cars and metro, and there's transitions that you can't do and transitions that you can do. And this is one of the pathfinding problems that goes through that huge graph. So, just to make this clear, those other calculations they're very weakly connected in terms of parallel processing. They're not exactly embarrassingly parallel, but they're almost embarrassingly parallel. You can really compute lots of these populations simultaneously, and there's only a few constraints here. But when you start to get to here, what happens is it's still sort of parallel in that every individual has to be able to look essentially at the entire network to route their day. So you thread them. So if you care, it's an SMP style. It's a single memory, multiple processor kind of a setting, but it's so much that it's very, very difficult to get these things to run, given that the paths on every one are so complicated. So we have developed techniques that treat these layers of modes and the trajectories through them as graph grammars, and essentially we take your activity list and we only show you pathways that satisfy words in a formal language that specifies the characteristics of your pathfinding. We can prove that those paths are always order n, where n's the number of nodes in your path that are turning points, calculations, and that we always find a near optimal path in that subset of the system. So why am I telling you that? I'm telling you that because that was an entire line of research that went on a very long time that, first of all, tells you a lot about the structure of the networks. A lot that wasn't known. But secondly, it lets you speed up the simulation, and it lets you put it on parallel machines. Okay, so once you've done that, if you just lay down everybody's plan through the network, what you get is the time-varying demand. this is in 5-minute intervals. For every piece of street and transport system in this case Portland. Now this is unrealized demand at this point because nobody's actually tried to do it. So we don't know if the supply will be in place, to be able to support this demand, but this is, given all of this motive, given where people live, given the constraints on economics and so on that define where they live, given their relationships among one another, and the ability of this system to deliver resources and timing, this tells you what the demand is. And the first time you calculate this, not too surprisingly, you get a result, but it won't do the following thing. The next thing is we actually calculate what the time delays are and the service that the roadways do, and we do it by actually putting you on a roadway. Now this is the first time we're really, to calculate this, there was a lot of work that was done in our laboratory and actually in Germany at that point in time. We're using cellular automata to treat traffic like granular flow. It's elaborated so it's very realistic, but the basic idea is that this is a huge parallel calculation where we calculate every single car in about 7-meter intervals once a second. The cars are populated with individuals, and we get very accurate representations of, like if you look at it this way, it looks like a little thing you could make pretty easily, but this is not made very easily. These flows are actually very, very close to what you observe in Portland by time of day, and we know who's in the cars, and we know certain things about them. We can track them around, and it's a very interesting capability on a lot of different levels. From a marketing point of view, you can know not just how many cars are going by here, but by time of day who they are, if they're late, things like that. We can even keep track of the tailpipe emissions because we can keep track of what kind of cars these people have, what their probable service characteristics are. We know what their acceleration profiles are, and we generate exhaust pipe level emissions profiles from these fleets of these vehicles. And it was used for some things from the Department of Transportation, which I won't go into. But anyway, what this gives you, if you look at this a different way, and I don't have slides of this, and I wish I did, is it gives you, if you look at a piece of roadway and just take one lane and just look at a piece that doesn't have any entrance points on it, you have conservation of cars. And it is a granular flow-like structure, so if you take flow and density, you get a relation that solves sort of like this from a fairly normal kind of a conservation equation. There's some modifications, but basically it's like that. When you actually simulate it, what you get is you get something that looks suspiciously like a phase transition. It's at least mixed phase flow at the maximum point. And so it causes the, and exactly how that works and how it causes time delays to change is a very interesting problem, and it's the reason we calculate these things directly. But that's a global structural property. It's pretty complicated. I'm hesitant to use the word emergent or complex, but I will simply say that if you don't calculate it this way, you don't get it right. You can calculate it and you can let people sort it out after you misplan their roads, but the fact is you don't get it really right. And what you can't do is calculate tailpipe emissions very well, which if you don't do it this way, which depend on the acceleration profiles, which depend on the mixed phase flow. On the other hand, you can also take trajectories through the CA and analyze these very, very simple integer rules we use to hop along the CA. You take a trajectory of successively occupied sites along the CA, and you can induce from that you have, it's a derivative feedback controller. So we're not calculating that, we're just calculating systems of integer adds. But what the semantics of it is, the thing that comes out of it, is a derivative feedback controller, which you can calibrate to the properties of drivers. So you have both things. You have a very primitive, fast-running calculation, which you can view in terms of its local dynamics and its global interaction structures, and you can calibrate both of them. You can calibrate the time delays and the fluid flows, and you can look at things like reaction time delays and stopping periods and things like that and make sure that those are right as well. So, and you can make sure that they're simultaneously right, but you're not writing but it's a very lightweight, very distributed simulation. So again, it's a place where a lot of detailed work in a seemingly fairly blue-collar environment has generated some really interesting stuff that doesn't just apply to cars. This doesn't just apply to cars at all, and I'll get to that later. Anyway, this gives you an idea. The place we looked at earlier is way up there, and there's a little square. I don't have a pointer, but it's about this big on this picture. And this is really the characteristic of the whole thing that we were calculating. At any point, and Portland is not that big of a city. It's 2 million people. It's a pretty big city. At any point in time, you can have up to about 600,000 cars on the road. Okay. Another way of looking at the same city, instead of looking at that stuff, is you can look at sites where people are and what they're doing. Because all this traveling is just taking you from one activity to another activity. I mean, that's the point of it. There's no other point to it. So, this keeps track of address by address. The colors are a very coarse grading of activity types. In this picture, we have many more activity types than this, but they've been partialed up into those colors. And the height is how many people are there. So if you look at this one, by time of day, the height doesn't really go down, but it changes colors, and that's because that is one of these places where there's apartments and shops and stuff. And so people are coming and going, but the total population in that place stays pretty high all the time, and the activities stay like that. So that's another view of it. Again, there's no place where you get data like this on this time resolution. The simulation synthesizes it, and it synthesizes it from things that range from traffic counts to land use surveys to marketing surveys and the census, and then a lot of simulating, and you wind up with information like this. This is important to things like understanding what electrical loads are going to look like in their dynamics. If you abstract all that out, at the end of all this calculation, if you take these individual traveler IDs, that these structures that have acquired all these characteristics as they've adapted themselves into everything from where they live to if they can make their way through to get to where they work and eat and stuff. You can do traveler ID by time, and if this traveler and that traveler, this is in the case of transportation, if they ever conflicted for the use of a resource, a piece of roadway, if they have to slow down for the other one, or if they got on the same bus, or if they were in the same car, if they ever interacted in the transport system, we put, at the point in time that they interacted, we put a dot. And then we just went through the simulation, and we just did it. We calculated their interaction neighborhoods. But this interaction was only for transportation. I mean, how these interaction structures look depend on what you're talking about. But this is what, and so if you take an artificial light, and you project it through, these are time trajectories of who this guy interacted with through time. And so you get this information. It turns out that, I'll tell you why I'm telling you, but that's a graph. It's kind of a funny way to draw the graph, but that's what that is. That's a big interaction graph through time that we have produced and now understand a lot better in terms of just the interactions themselves, and we can decompose by using the simulation and the steps of leading to it how individuals interact with one another from the point of view of the transport system. And what I told you earlier was that's the thing that turns the infrastructure on. That's the thing that causes these synthetic individuals to start going places and doing things. So you have to do the activity-based thing. So here's some other stuff you get out of it. This is the number of people at home. I won't go into what the colors are for. It really doesn't matter. It's by certain classes of what they're doing at home, but by time of day. This is not data we collected. Again, this is data that, because it doesn't really exist this way, it comes out of simulating these activity structures. Here are people at work by time of day, people in shops. So you get large... You start to pull out, you start to know where people are and what they're doing. So I pick a non-contentious or relatively uncontentious demographic variable, age, and I say, if you're, in this case, this is an average one, if you're some age, what is the distribution of ages of people you come in contact with? But I could say, if you're some income level, what is the income level of people that you come in contact with? I can ask for a big manifold if you come in contact with. I can ask questions that really have a lot of political baggage associated with them about who you come in contact with. So if you're between 0 and 1 years old in Portland, what we're saying is in the first graph, that's the age distribution of people you come in contact with. It's sort of the same up to, this is 0 to 5, but the numbers are changing, if you could see the picture, which I see you can't. What happens when you're 16, though, is kind of interesting, is you only hang out with 16-year-olds. And your family, pretty much, and there's some, and it doesn't change much through those years, but when you enter the workforce, it changes again. Now, I want you to realize we didn't try to do this. I mean, this comes out of just putting the right people in and having them do the right things, and then you figure out who they were in contact with, okay? I mean, I guess you could call that something that there would be a better way to do, but I don't know how to collect this data in any kind of reasonable way. To go around and, while you're at work, say, how old are you? Keep a diary. I mean, I guess we could all get Docomo, those little things, and it would be broadcasting your age. But I mean, those things are all, they don't make sense. I mean, this is a way to extract information. This information is latent in information we already have, I guess is what I'm saying, except you have to add all this. It isn't a data mining problem. It's a synthetic problem. You have to do stuff to make it come out. Anyway, so when you're younger, you don't have kids, and then you get a little older, and you do have kids, and that starts to go up, but you're still at work. And then you get a little older, and then the kids go away, and I don't know. So the point is that you can explain this stuff away, but age is just a placeholder for all these demographic variables. Now, what this picture is this is it's a shattering graph. We're talking about the size of the largest component. These graphs, you can look for components in them, just exactly like Lord May was talking about. You look for components in them. We don't prescribe what kind of graph they are. Depending on the interaction structures, you get certain kinds of graphs out. This particular one is not the traffic graph. This is physical proximity graph for contagious disease, an aerosol-borne style contagious disease. It turns out, if you just start taking out the individuals that have the highest number of interactions, you just start taking them out. You want to say, have I broken down the components that the disease will move over? You have to take out 80% of the people before you get the thing to shatter. And the reason is because that when you go back and look, that particular kind of a graph is an expander graph, and it's just an incredibly robust thing, and it's interesting. It's important, actually. It's why society can function whether you're sort of there or not. You know, I mean, we could all get run over by buses. This whole room could get run over by buses, and it'd be real sad, but things would go on. Okay, so those are other things that we get out of this. We get these interaction structures, and we can then evaluate the characteristics of the interaction structures in really a lot of detail and begin to understand things. And we'll get to epidemiology soon enough. But you can couple these simulations with other simulations, and you can start to do a thing where you append extra state variables to these individuals. So from other information, I can append what kind of digital devices you own, and I can append information about what it is you're doing when you use them. And I can attach it to you in this other simulation where I'm keeping track of what you're doing, and I'm keeping track of who you are. And so from that, what happens is we can place you very accurately in the correct location in the right activity type when you begin to use that particular telecommunications mode. And so at that point, if you're in radio land instead of wireline land, you can be in wireline land, but if you're in radio land, and these are extremely simplified because, of course, broadcast radii are not radii, but you have interaction in radio frequency. So now you're interacting by sneezing on each other, you're interacting by being in their way in traffic, but you're also interacting in radio frequency, and they're all coupled, but they're not the same dependency structures because what's interacting is different. And so at this level, if I turn my radio on, well, if this guy turns his radio on and this guy turns his radio on, then the medium access layer has to fight for frequency to keep them separated in frequency space so they can, these are base station antennas, and if you're talking about cell-style telecommunications, it's going to go up into the wireline network, and then you're interacting with different resources on a different network up there. These are really complicated, and they're actually even not all that well understood. The protocol stack in IP protocols is a very, let's just say it's an evolutionary object, and nobody really understands that object. We published a paper a few years ago on interactions in the protocol stack, and when we first tried to publish it, we couldn't get anybody to publish it because they didn't want to hear about interactions in the protocol stack. Because that means the semantics isn't defined by studying the protocol stack. I mean the layers. You can't like work on the MAC layer on team A and work on the routing layer, link layer on team B and come together and have a thing that works. It doesn't work that way. They didn't like that. So anyway, so you have all these different networks. It's sort of like having walking and bicycles and driving networks that you have to show. But so this guy's ability to move information he's going around down here, he's moving around up here, it's causing things to go on up here, and it's changing something else somewhere else, and the interaction structure is real complicated and time varying over very short time intervals. So again, I'm not going to go through this in detail, but we assign device. So there's the output from all the little guys running around. We give them devices. We give them telephones, we give them cell telephones, we give them these things, we give them whatever digital device you have. They can be real, or it could be a marketing survey for a new technology that has a targeted demographic and you want to see how they're going to use the system, or you could be putting in a new base station, you want to see who it services. Device generator from that, because the activities, and I told you, like for example, this survey, this is called the Yankee Group survey, there's another one as well, but you can get out what it is they use them, so you start the sessions. I'll talk about the topological structure of the network. Then you simulate it down to individual packets. We don't simulate the payloads, but we simulate every packet. So in a place like Washington, D.C., for example, that means like 10 to the 12th, 10 to the 13th packets an hour. So that's the size of the simulation. That's the traffic size. We do sort of the same thing. You can sort of recognize there's kind of a theme here. We had this coordinate system, and now it isn't just John Doe sitting over there at this place. It's John Doe. And John Doe's intention now gets attributed to the activity of his seemingly inert object, his cell phone, which is now imbued with the motive structure of John Doe. So it's a thing that can't have motive, but it can be attributed with John Doe's motive, and it can be given places and have what amount to his desires attributed to it. And he calls Jane Smith, and he changed age magically, and I don't know how that happened. But anyway, so we can give him a particular digital type, and we wind up with the appropriate person to call, and we set up a session. Lots of sessions get set up, and so at a snapshot in time, what you have is a distribution of wireless devices. You have their interaction in frequency space. There's also things like buildings and trees and stuff in there which change those shapes. What you wind up with is a graph. And so an instant in time in Portland, that's an interference graph for cell phones. And I'll show you what I mean by that, but that is edges between individually operating cell phones that have a MAC layer, trading, and sharing frequency. Then you lay down the wireline and built infrastructure. This is fake, so we don't cause lots of angst. This is actually a Voronoi covering of base stations. It's actually not so easy to get this information. To get the base station locations and operating modes in the United States, they quit filing this with the FCC for, some sort of free market argument. And so you have to do other things to get these. But you can, in fact, pull this information together and you get coverage areas. And then what you do is you drive the vehicles, this traffic, and move people place to place, and you tell them when to turn on their phones. And you get this sort of a thing where these are, as you get closer, you start to be able to see them. I sort of started too far away and I didn't cut the film. Those are actually mobile starts. And the time resolution of this is a lot less than a second, so it looks like it's going on a long time, but it's actually being real accurate about where the mobile starts are going. And so what you get from that is the ability then to, this starts to be redundant at some point. You start to see that there's a theme. You can append structures on top of an underlying dynamic, and then you can induce the dynamics in the network that's coupled with it. And I just want to make sure that I'm saying that because the theory then has to support taking one of these dynamical systems and making some sort of a product relationship with another one of them, and you have a joint phase space, for example. and you have a combined interaction structure, and they get really complicated, so you have to have pretty powerful films. So these are base station loads, and the color indicates the predominant character of what's going on, what the kind of service that's going on, whether it's residence to residence, personal communication, or whether it's business communication at the point in time. And you find that those things actually are different. And I don't know, but I don't think there's information about loadings on base stations. I don't think there's a lot of information on loadings by use type on base stations, and you get it out of these simulations, at least. So here is what an interaction graph looks like when it's evolving, and this is an interference graph, interference structure for cellular phones in traffic, in vehicular traffic in Portland. Okay, and what you get out at the end, I don't know how to characterize what you do with a trillion packets, but here's one of the things you do is you look at what the packet performance is. This is number of packets received in percentage by how much you turn up your radio. It turns out if you turn your radio up too much, you interfere more. If you turn it down too much, you don't connect, so there's a convex function that tells you that. But what these two lines tell you is that when we use the transportation simulation, the high fidelity thing, you get very different results on how the service levels work than if you use a random weight point model, which is a common thing to actually do right now to try and characterize how a mobile system is going to function under some argument that it's too hard to know the details of what the actual movements are, so you use a random weight point model, sort of molecular dynamics kind of a model, and you calculate that way. Well, it turns out that you don't get the same idea of what the performance of the system is if you do it that way. And it's demonstrable that you don't, and there's ways that you can understand why. And given the last talk, this is kind of interesting. One of the issues in epidemiological modeling, I don't have to tell you now, is the derivation of R naught, of this first parameter that Lord May was talking about, R0. If you think about it, what you realize is what you've combined in that equation is the social network and the activity of the disease. And so there's no way, so if you were alone in the desert, R0 would be, 0. But it's the same disease as if you were in here, it wouldn't be. And so from the point of view of epidemics, it's probably better to try and separate the population structures from the disease activity to understand better what you might do to change the population structures to affect how the disease moves in it. Because you can't use the same R0 because everything you do, it keeps changing R0. And if you make people stay home, you changed R0. So we're going to use these structures, and you start out and you sort of say this. I mean, here's a family, and you can't see the lines, but there's lines between all the individuals in this family of 4. And then they do things during the day in those activity types, and then at some point, I guess there's 4 people back at home. I mean, this is a cartoon, so forgive the cartoon, but you get the basic idea. And when they come to those places, they come in contact with other people. And those people also have structures like this. So what the simulation is going to let us do is calculate, obviously, these interaction graphs where we define when it is we say they've come in contact. So it could be that you have some likelihood of being within 20 meters for more than 10 minutes. And then we put an edge. Otherwise, we don't. That could be a criterion, if that was the important criterion. And we would derive that from looking at things like, viral concentrations and how long it would take to get a certain kind of a dose. And then we'd figure out what that time interval needed to be, and then we would put it there. And so you get these things. So you wind up with, say at a point in time here, this is actually a 3-level small world graph that came out of Portland simulation for one family of 4, where one of the family members is an infant, and in the time period of the simulation didn't leave the home. The other people did, and this is the individuals that they came in contact with, and the individuals that they came in contact with, and so on. And you can look at, and these are the pathways that contagious diseases that are aerosol-borne, because these are proximity-based graphs Those are the pathways that the aerosol-borne diseases move on. And so if you want to stop the aerosol-borne disease, you have to break this graph, and you have to do it by either taking people out of the graph or you have to do it by immunizing them. And so then you have to have them immunized in time to stop the path that they're trying to find to be active, or you have to take them out soon enough, and so on. So we did a lot of work on, for example, smallpox and some other things. But with smallpox, basically the way the story goes is this, is you don't have much time or it's going to really take off. So you have to do things like have these very selective kinds of ways to find who you're going to vaccinate because you don't have a lot of time. You may have enough vaccine, but you have to, you're talking about a lot of people. And every person takes a little while. It's like a logistics problem. It's like an operations research problem. I mean, how many vaccinations per unit time can you do? Further defines who you have to go to. So you model those sorts of things, and you get this is the sort of thing that comes out of that. This particular one is not real sensitive, so I'm going to show it to you. But there's a vaccination strategy that you can see here. There's a quarantine strategy that you can see the people associated with it. And this is a baseline. And the reason I show this is one of the things I'm not talking about, which is a different talk and which is actually a more interesting talk to me, is what people use these simulations for. Because there's an idea that what you use them for is to predict things. And depending on what you mean by predict, that's probably not what you're going to use them for. But this is a baseline. This would never happen, but it gives us an analytical basis to study options of things you can do. So this is just one option. I'll run this little movie here. What you're going to see is, and we heard about this, there's a, doesn't seem to be working. That's weird. Sorry. It was just working. I was just looking at it, so I don't know. I can't explain it. Let me see if I can make it work. There we go. I don't know why. So at the beginning, they're the same because all these infected people are running around, but they don't know they're contagious. They don't know they're infected. And at some point, so there's nobody's dead and have the same number infected. At about day, I think it's day 11 or 14 or something, it's pretty far, people start showing up. So this vaccination strategy in the quarantine, in hospitals and things, they're sick. And the quarantine vaccination strategy kicks in. And now you start to see differences in dead in the baseline case, in this particular activity case. And when it runs, what you're going to be able to do is understand, in this particular case, just how many people would die if you did that, or what would you expect. You run it a lot of times, you get some sort of idea of the effectiveness of that, as opposed to other things you could do. You look at their costs, you look at how many doses were used, you look at all kinds of things like that. But you can also go back and see what's happening to those graph structures and what's happening in this disease. And if there are selective populations that are affected. And it turns out, I mean, you would expect that if something goes like this, at some point, the distribution of infected people in terms of demographics equals the demographics of the people in the city because, right? So we've looked at, in certain ones of these quarantine strategies, that never happens. It never converges because the quarantine strategy breaks things down before they mix enough with the rest of the thing. And so those are actually really desirable states. So it turns out there's a lot of interesting work you have to do to figure out how to measure that. It's not easy to measure differences in distributions of wildly equal size. And subpopulations that are infected compared to the entire population are. So you have to have measures that are insensitive because you get, if you make them, they're size sensitive, you wind up with results that make you think they're significant and they don't mean anything because they're just a noise in the measurement. So there's also stuff on the outside looking in on these things that are basically statistical problems and measurement problems. They're also very interesting. So in this case, if you took these actions, you'd lose 435 people, and at the end of the day, you'd have 37,000 people vaccinated and 36,000 of them in some sort of quarantine. This wasn't quarantine, actually. It was isolation strategy at home. And over here, basically, it was, compared to baseline, you get the basic idea. So you can try different things here, look at cost, benefit structures, see who's affected, what functions would be, can you keep this disease away from the demographic that manages the power plants or something, or the kinds of questions that actually matter. And we've done a lot of applied work with this. I mean, we actually deliver this stuff. It's interesting, you know, you deliver this information to these people, and they don't want to lecture on how to use this information, which they really, really need, and then they do whatever they want, and you just, it's amazing what they do with it, actually. Okay, so we also have, I told you, in a very similar setting, now we know where people are going. This focuses more on where their activity locations are and what they're doing. This picture, then, where you are and what you're doing, gives us a good estimate of what your demand for electrical power is going to look like. So we can look at markets associated with the delivery of electric power, and we look at competing markets. And so a bilateral market, in case, let me just tell you what a bilateral market is. A bilateral market is a market where, long in advance, a company some entity that is a large user of electrical power makes a dedicated contract with a distributor and a generator to deliver power to them for their purposes on a guaranteed basis at a guaranteed price. And so they can lock up big pieces of the network. Now, if they lock up too much of the network, then nobody else can use it. So there are regulations in their offices, at least in the United States, about how you can do that. Then there's a forward market, Poolco market, and they trade power, you know, day ahead, 2 days ahead, month ahead. There's long-term markets, year-ahead markets. They trade power on those kind of basis. They trade power, meaning you buy contracts to deliver power at a given price. And then, when the estimation on the part of the generators and distributors for demand in particular areas is just wrong, then you have a spot market. And basically, spot markets are very accurate indicators of the difference between the estimation procedures and whatever it is that's going on here that is causing demand to deviate from those procedures. So it's a really good idea to watch the spot markets if you want to do this sort of thing. So what we use this for is actually to monitor if there are changes in activities in the population. The cascade through, if you had somebody, there was a warning that, I don't know, somebody was going to do some evil to the population, and they did it on the news. And then there was a government official made a statement to calm the population for whatever reason, or they said do X. And the question is, are people doing it? And you want to know before it's like really obvious to everybody. You want to have indications that either your pacifying message made things better or worse, or they're going over there instead of over there. You want some indications. It turns out you can watch spot market prices for power distribution and get a really good indication if there are deviations in activity structures that would give you, and that is a cascade of dynamics through really a lot of things, right? I mean, there's all kinds of things interacting, and it's just a really interesting sort of class of problem. You can also, though, analyze how different kinds of contract structures affect the stability of the physical system itself, which is also really a complicated dynamical system. And you can drive one of them unstable through market actions. There's actually an office, I don't know what they're called here, but in the United States they're called independent system operators. It's an office that, and their responsibility is to assure that price-cleared contracts are physically realizable. And they do it every day, but I mean, think about that. That's a really hard problem to ask somebody to solve here. I mean, these things close really fast, or a year in advance up there. I mean, how you destabilized or changed this system is a really interesting problem, and so that there's a lot of concern by certain people that we would be working on such a thing as a financial market, because we're supposed to be working on much more sort of straightforward things associated with security. But if you want to understand how the population is starting to move, then a measure of mood is market price, and it's a pretty good measure. And electrical power is just connected to everything, so it's a really good marker. It's an incredibly interesting one, and it has value outside this project, obviously, for other kinds of things. So, no matter what it is we're talking about, whether it is you're breaking interaction structures that are possible because you change the transportation network, or you take down power lines, or what you have in every one of these cases is you have local entities that we've composed, and we've done it in this way I keep telling you about. You append state, you attach dynamics in certain ways that You allow feedback to pass between the dynamics. You do it in a systematic way. And one of the issues is my computer as a dynamical system itself set up to, this is the modeling question, to mimic this other distributed dynamical system? That's one question. The other question is, can we do it fast enough to have it make a difference? Is there another way to do it? Could we just aggregate this? Or those kinds of questions. It all comes down to interaction structures, their temporal variation, and the dynamics that compose these things and that are composed from them. I mean, there's a dynamic of a disease. So transportation and activity structures generate this graph, but then the disease dynamics move on this graph. Radio characteristics and modulation generate this graph, but then packet dynamics and packet traffic characteristics move on that graph. That thing evolves over very small timescales. Urban evolution people, they like to tell you how the streets evolve and so on, and they're designed in ways and it's absolutely true. You can treat it like a dynamic evolutionary process, and then those things move on it. And if you interrupt that process, or if you change it, or if you change the land use, that changes. And it can change things like this. It can change where you need base stations. So it's all about composed local interactions. It's just that local doesn't mean one interaction characterizes everything. They're not the same kind of graphs. This is a very difficult to fracture graph. This is a sort of intermediate graph. It's actually fairly easy to fracture that graph, but a lot easier than that one, for sure. That is easy to screw up, as we all know. I mean, traffic stops all the time because if you do anything to this thing, the dynamics just lock up. And electrical power systems are also incredibly fragile from this point of view. So, but it's all about that. Even though the underlying system we're talking about here is in some sense the same one. Okay? There's lots of different kinds of interactions going on simultaneously in lots of different ways, and they all characterize what you mean. So how do you think about formalizing this thing? And now I get to talk about the part that I'm actually interested in. I really never thought that I would care about traffic. I really feel kind of strange having to follow Lord May with anything to do with epidemics. Similarly, in other settings, there's people that make their life in traffic and other things. And we have, I guess we're dilettantes, but I don't feel like a dilettante. We really spend a lot of time trying to figure out what these things are. But we're primarily computer scientists and theoretical computer scientists. And so the real thing that drove us is that we want to know how these composed systems work, and we want to understand how that has to do with computing. And so, a local interdependent function is associated with each vertex as a local mapping. And by local, what you literally mean is that it takes the values of its neighbors. That's what you mean by local. This is a cartoon of a picture. It really doesn't have to look like that. A local function returns a new state based on the states in its adjacency, and it can, including its own state, depends on there are different kinds of systems. And its value then will depend on the order in which you evaluate those mappings. And this is part of the thing that makes it really interesting. Is when you wind up with complicated graphs, what you do is you have to factor it into pieces that don't matter about the order and pieces that do matter about the order to understand how inherently parallelizable these systems are. And if they're completely sequential and there's 10 to the 12th pieces in it, then you can't calculate it, basically. I mean, it's more subtle than that, but that's basically what you want to do is understand how to get this down on something you can do. Where the questions are hard, you have local information, and the question is, what is the more global system dynamic? Or how does one global system dynamic flow into another system dynamic? So, a sequential dynamical system is the thing we've created. It's a mathematical object that we've created. It's the object of study. Its general case is sequential. They can be parallel. It depends if they're factorable. It has 3 pieces, and it's slightly redundant, which, if you don't notice it, I'm not going to explain it. I'm just going to say it. It's a finite underacted graph that characterizes interdependencies among vertices, a collection of local maps associated with the vertices of that graph, and a permutation of the vertex set, which means the order of evaluation of the maps. So here's a really simple one. It's got 4 edges and 4 mappings. The mappings are symmetric Boolean functions. In this case, it is logical NOR. That's the truth table for logical NOR. The only time you have a 1 as an output is if the other guys around you have 0. So in every case, there's 3 values associated with your value and your 2 neighbors. That's what those 3 things are. And then what you output, if given those conditions, which is all the conditions, that's what you output. That's logical NOR. If you evaluate it in the order, if this is 1, 2, 3, 4, and you evaluate it 1, 3, 2, 4, if that's the order you use, this is the phase space of that system. If you evaluate it 1, 2, 3, 4, that's the phase space of that system. They're completely different systems. So there are some things that, I mean, you have to be careful. So you can have, okay, let me just back up. A lot of times in simulation, from a practical point of view, they'll spend a lot of time, practitioners will spend a lot of time worrying about getting every agent perfect. They'll interview people, they'll knowledge engineer, they'll do a lot of stuff. But it's not so easy to also be so careful with interaction structures. The order of which, the structure of which changes the order in which you have to update these things to get certain, are you in this system or are you in this system are completely different things. Keeping the objects right doesn't guarantee that the system is right at all. So the question is, how do we deal with equivalence? When are 2 things equivalent? Well, they're going to be equivalent when their dynamics are measurably equivalent in some sense. So some of these can be due to relations in the dependency graph alone. So you can have 2 systems that are exactly equivalent, and it only depends on this particular thing that causes them to be equivalent has nothing to do with what the local mappings are at all. And I'll give you an example of that. I mean exactly equivalent. Other times it'll only depend on the functions, and it has nothing whatsoever to do with what they are. So this is called a neutral network. Neutral network. It's a concept that actually comes out of sequence to structure mapping in biomolecules. This phrase, neutral networks, comes out of it. I don't know if you can actually see. There's vertices at these places. Each one of those vertex points is a permutation of some number of vertices. It's one of these things I was talking about earlier. So it's in order, the entire SDS in the order in which it was evaluated is a vertex. And that's one of these vectors is the order in which it's evaluated. So the difference between these 2 orders is exactly one location is flipped. Okay, now if in the underlying dependency structure, the 2 vertices that you flipped did not have an edge between them, then you didn't change the system when you flipped it at all. And so it's evolving phase space. Black is 1 and white is 0, and a vector of 1 through 10 is across here, so that's the time history of the states it's entering into if you just successively evaluate it. When you flip it, that picture won't change. And so all the things that are like that, where you have adjacent things that are flipped and they do not have an edge in the dependency graph, then you stay on this network, and those are neutral shifts. But if you flip one and it does have an edge, then you're going to flip onto another one, and so it just turns out you can study these networks and you can ask algebraically, you can ask questions like, do these structures come close to one another? Are there islands? Are they everywhere close? Are there pathways where you can only get from one by passing through a particular sequence of other ones? And there are answers to those kinds of questions as theorems in this class of systems. So there are questions that you can ask about exact equivalence that have nothing whatsoever to do with what the function is at all. They only have to do with what the dependencies are and how that affects your ability to evaluate the functions. And those things are real exciting because those things are the kind of syntactical objects that you can use to parallelize simulations. When things flipping in order don't matter, you see, then you have situations where you can do things like factor these things, put them on lots of processors, and speed them up. So, on the other case, certain kinds of equivalence properties and other kinds of properties depend only on the functions and have nothing to do with them. And this is an example. There's the theorem that shows that the only sequences of these kinds of systems, okay, let me say it backwards. If you have NOR functions or NAND functions as your local maps, then the system has no fixed points and it doesn't matter what the graph is. Period. And there are no other functions that will do that. Which is kind of interesting because they're universal functions from a computational point of view. So But the point is that if you have a system that is composed, if the model you have is equivalent to logical NOR, and I won't give you examples because there are situations like that. They actually turn out to be game-like situations where you're sharing resources, interacting NOR functions act like cooperatively, cooperative players in a game. Those systems don't have fixed points. And they can also be equivalent in the sense of isomorphy. Here's an SDS that's a 3D cube, just to give you an example, and it has, if it's NOR functions that it has, this is its phase space. If you map it onto this tetrahedron, where you're taking corners and mapping it onto this tetrahedron, then this is this phase space, and if you sort of look at the first half of that one, this is carried over. So this is a reduction of that system, and there's a morphism that you can, there's a way to define morphisms to map one onto another. So that's really important if you're going to map one dynamical system onto another, like a model onto a distributed machine, for example. And you want to guarantee that just the act of doing that has maintained the basic dynamical system. This is the sort of thing that you can do. Or you want to reduce model just because you want a parametric reduction so that you can do something. These are the kinds of results. And you can demonstrate equivalence. How can you build them up this thing where, well, we just add on another demographic vector. We know your age and stuff, so we're just going to know what your cell phone is too. And we just keep doing that. So how can we do that? This particular case is a Cartesian graph product of SDS. There's a simple line SDS. There's one. You take a graph product, you wind up with this sort of thing, and it has exactly the kind of phasic structure that you want, and it gives you a concatenation operator on how to build up the internal structure, basically, of this object, which is now a collection of different kinds of rules. Because at one place you interact one way, at another place you interact another way, at another place you interact another way. They build up into this really complicated product rule interacting with other complicated product rules, and we know how to characterize that in terms of the composite SDS, and there's things that you can prove about this in terms of embedding of these other phasic structures I showed you about. They're embedded in here, and then there's other places where they're altered. From a computational point of view, I'm almost done. From a computational point of view, you remember the tapes, the black and white pictures in the neutral networks. You can take the pre-image of this SDS, treat it like an input tape, and the image of the SDS, and treat it like an output tape, and then the SDS can be proven to be a universal Turing machine. In any universality class you can define, there's an SDS that will do it. And what this tells you is, at least from the question of sufficiency, the process of simulating is it's sufficient to cover the class of computing. So interaction-based computing is sufficient. It isn't necessarily necessary yet, but that's one step in whether it's optional or not. They're an extreme form of distributed computing. I guess that's pretty obvious. But this connection allows you to connect to algorithm theory. Now, what's interesting about this is then you can talk about this SDS, which is just a bunch of local maps and doesn't know what it is this algorithm. And you can write down the algorithm. And then you can prove a bound on the algorithm, like time-space bound on the algorithm. That's the algorithmic semantics of that sequential dynamical system. And the algorithmic semantics has properties like time-space complexity properties. And those properties will bound that sequential dynamical system. In other words, they will constrain it. And so there is a very interesting and different sort of view of what you might mean by emergence and how it applies to understanding what you mean by computation. It's like an emergent computation with specifiable properties that you're not programming at all. It's like side effect almost, things that you can specify. So that's the basic idea, is SDSs can be viewed algorithmically, and when you do that, you can prove some theorems, and they're universal for all natural space complexity classes. We have normal forms. Basically, we can build SDS compilers. So you can take a big thing and turn it into collections of little things, which is important if you ever want to compute them. You can test to see if they're equivalent. And this is the part that comes to necessity. Reachability for SDSs is piece-based hard in certain circumstances that are very primitive. And basically what this result means, combined with the dichotomy result here at the bottom, is this, is it means that there are problems that nothing smaller than an SDS will compute. And they happen pretty early. So you can do it another way, but it's not going to be any smaller than this. And it might be more expensive to collect the data or something. You see, it depends. And so the question then is simulation optional? Can we begin to get a handle on what we mean by simulation? Can we be more rigorous, and can it have any practical use? These are all practical problems done for real customers and have real needs, and it drives this theoretical program. And it really does cut straight to the problem at the basis of, is there anything in this that is something other than trivial? Is it just a programming exercise where you knowledge engineer things and then program a lot? Or is it something else? And the idea to all of those things, does it relate to dynamical systems? Does it relate to the issues of complexity, the classical issues of complexity? And the answer to all those questions, I think, are in the positive. And I think you're really informed by things like what you mean by agency. I think there's a lot of richness and stuff in here, as well as practical value. And so I guess I leave with this, is that a lot of the concern about what simulation might have been, or maybe still is in a lot of places, is something that might be assuaged a little bit by this. I think we can use it, and I think we can make a lot of progress for it. And we can do things that we can't otherwise do at all.